NASA's latest daily update on 3I Atlas dropped today, and once again, the line everyone is quietly waiting for still isn't there. No mention of stabilization, no sign that activity is settling into a final, predictable pattern. Instead, buried under careful technical language, the message is the same as yesterday. 3I Atlas is still not stabilized. If you've been following this interstellar object and wondering whether it's finally calming down as it heads away from the sun, today's data gives a very clear answer. It isn't. In fact, today might be one of the strongest confirmations yet that we're still in the middle of this story, not the ending. Stay with me, because the numbers released today quietly say a lot more than they seem at first glance. Around the internet right now, you'll see a lot of familiar headlines attached to this object. The comet might break. Possible fragmentation. NASA is concerned. Something strange is happening. Most of those narratives are built on one or two isolated data points taken out of context and pushed as conclusions. The headlines are scary, but the depth behind them is often very thin. The day started like every other routine check. New brightness measurements, fresh positional data from ground-based observatories, updated images from both telescopes and spacecraft instruments. Nothing about the schedule suggested anything dramatic. This was supposed to be just another point added to a smooth, predictable curve. That curve is something astronomers know extremely well. After perihelion, the comet's closest approach to the sun, activity should decline. Less heat means less gas sublimating, less dust being lifted, weaker jets, and a steady drop in brightness. The light curve bends downward. The coma softens. The tail spreads out and fades. This is basic comet physics. We've seen it dozens of times. On paper, 3I Atlas should be doing exactly that right now. But when today's brightness data was plotted against the predicted post-perihelion decline, the curve didn't behave. Instead of sliding downward, it flattened. The comet is dimmer than its peak, yes, but it is still far brighter than it should be at this distance from the sun. That's the first warning sign. A comet that is stabilizing follows the math. A comet that refuses to fade on schedule is telling you something inside it hasn't finished responding yet. If this extra brightness were just leftover dust from earlier activity, the inner coma would look washed out and diffuse, a fuzzy cloud slowly dispersing. But that's not what today's deep stacked images show. Instead, the inner coma still has a sharp core, surrounded by a faint but distinct arc, a new shell of material that simply wasn't there a few days ago. That arc is important. It's essentially a timestamp made of dust, the outer edge of a recent outburst that's still close enough to the nucleus for its structure to remain visible. Old material would be smeared out by now. This isn't old. This is fresh activity. Farther out, the tail tells the same story. It still has a narrow, well-defined spine, a bright central lane fed by a focused flow of material. Dying jets don't look like this. They spread, weaken, and blur. Today's images even show a slight thickening on one side of the tail, like a side fan of material has strengthened again. That's not the geometry of a system shutting down. That's a system still updating itself in real time. Then comes the rotation data, and this is where things get especially revealing. To track how 3I Atlas is spinning, astronomers monitor how its brightness rises and falls over hours. As the nucleus rotates, different active regions come into view, creating a repeating light pattern. For a stabilized comet, that pattern repeats cleanly. Peaks arrive on schedule. The shape stays consistent. It's predictable, almost boring. You can fold today's data over last week's rotation period and everything should line up. Today, it didn't. When the new photometry was folded over the previous best-fit rotation period, the peaks drifted. The main maximum appeared slightly earlier each cycle than predicted. And a secondary bump, once faint and irregular, has become sharper, stronger, and consistent. It now appears at the same phase every rotation, almost rivaling the primary peak, like a second heartbeat that suddenly decided to make itself known. To make the data line up again, the rotation period had to be shortened slightly. That means the comet has spun up again, not dramatically, but measurably. And that stronger secondary peak tells us something critical. A second active region is no longer occasional. It's locked in. It's now a permanent contributor to the comet's behavior. So brightness isn't stabilizing, structure isn't fading, and the spin isn't settling either. Now we get to the part that ties everything together, the orbit solution. Every new positional measurement gets fed into sophisticated models that calculate exactly where the comet is and where it's going. Gravity handles most of this easily. The sun, the planets, their tiny tugs, this is well understood physics. The complication comes from non-gravitational forces. When gas and dust blast off the nucleus, they don't just drift away, they push back, like a tiny rocket engine. Individually, these pushes are small, but over time they add up and measurably alter the orbit. If 3I Atlas were calming down, that extra push would be fading. The non-gravitational term would shrink toward zero. Eventually, you wouldn't need it at all. The orbit would become purely gravitational again. Today's solution still needs that push, and not only that, it needs it in a slightly different direction than yesterday. Using yesterday's parameters, today's observed positions don't match the predictions. The residuals lean systematically to one side. That means the model isn't just noisy, it's wrong in a specific way. The thrust vector has changed. Its direction has shifted. Its strength remains too large for a calming object. 3 independent measurements now tell the same story: brightness that refuses to fade properly, structure that shows fresh activity, and an orbit that still requires a changing self-push. Add in a rotation period that keeps drifting, and the picture becomes very clear. This is what not stabilized actually looks like in real data. When you put all of this together, the behavior of 3I Atlas starts to make uncomfortable sense. The key detail is something that's easy to forget when we talk about orbits and light curves. Heat does not move instantly through ice and rock. It moves slowly, sometimes painfully slowly. The close pass near the sun didn't just heat the surface and move on. It launched a thermal wave that has been traveling inward ever since. Days, weeks, possibly months. The outermost layers reacted first. Volatile ices sublimated rapidly. Dust was lifted, jets flared, and the coma took on those strange, chaotic shapes that caught everyone's attention near perihelion. But 3I Atlas isn't a smooth, uniform snowball. It's an interstellar object, formed around another star, under conditions we can only guess at. Over billions of years drifting through interstellar space, it was bombarded by cosmic rays, struck by micrometeoroids, and slowly fractured by long-term thermal stress. Inside that nucleus is a layered, cracked structure, not homogeneous ice, but pockets of volatile material buried at different depths, each with its own temperature threshold. Each pocket is effectively waiting its turn as the heat wave continues migrating inward. When one of those deeper pockets reaches its critical temperature, the response is sudden. Ice sublimates, gas expands, pressure builds along ancient fracture planes, and eventually that pressure vents. Crucially, this process doesn't care that the comet is now moving away from the sun. Once the heat reaches a layer, the physics takes over. Every time one of these buried reservoirs turns on, 3 things happen simultaneously, and all 3 match what we're seeing in the data right now. First, fresh gas and dust are injected into the coma. This replenishes material that should otherwise be thinning out. That's why the brightness refuses to drop along the expected curve. That's why new shells keep appearing in the inner coma. We're not seeing leftovers, we're seeing new supply. Second, jets from new locations apply torque to the nucleus. These jets are not coming from the same surface regions that were active earlier. They're emerging from deeper, previously dormant areas. Each new jet slightly alters the spin state, speeding it up or changing the balance just enough to shift the rotation period. That's why the light curve peaks keep drifting. That's why the secondary brightness peak has grown stronger and more consistent. A new active region has joined the system, and it's now contributing every single rotation. Third, the direction and magnitude of the non-gravitational force change. Every new jet alters the net thrust on the comet. The result is a self-push that doesn't just weaken smoothly, it evolves. It shifts direction. And that's exactly why the orbit solution still requires a strong, changing non-gravitational term. From the outside, using nothing but measurements, 3I Atlas looks like an object that is actively resisting simplification. It refuses to flatten its light curve, it refuses to lock in its rotation, it refuses to settle into a clean, fading tail. The models keep having to chase it. If we could somehow see inside the nucleus, we wouldn't be watching chaos, we'd be watching adjustment. A stressed body trying, and not quite succeeding yet, to reach a new equilibrium after experiencing more heat than it is seen in billions of years. Now, it's important to be very clear about what this does not mean. There is no confirmed fragmentation, no second nucleus breaking away, no debris chain trailing behind like breadcrumbs, no sudden catastrophic brightening that would scream breakup in progress. This is where speculation-heavy narratives usually take over. Unusual behavior gets immediately labeled as fragmentation or failure. But real breakups leave very specific signatures, and those signatures are not present here. This is not evidence of imminent disintegration. But it is also no longer consistent with a quiet, predictable outbound comet. Point 3I Atlas is not doing that. Instead, we see a rotation period that continues to creep. Activity that pulses instead of declining smoothly. Brightness that refuses to obey the inverse square expectations. And a self-induced orbital push that remains both necessary and variable. This isn't speculation. These are direct measurements, reported independently by multiple observatories and instruments. The numbers agree with each other, even if they refuse to behave. From here, there are really only two possible paths forward, and right now the data doesn't tell us which one we're on. On the first path, the thermal wave finishes its work. The deeper volatile pockets exhaust themselves. Each new pulse of activity is weaker than the last. The added torque diminishes. The rotation period finally settles into a stable value. Brightness begins to decline in a way that matches the models. The inner coma loses its sharp structure. The tail becomes diffuse and faint. The non-gravitational forces shrink until they can be ignored. Not stabilized turns into stabilizing, and then eventually into inactive. 3I Atlas fades into the background, a quiet interstellar relic, drifting back out of the solar system after a brief but fascinating visit. On the second path, the pattern continues. More late-stage pulses, more unexpected brightenings, more torque applied to a nucleus already stressed by fractures, spin changes, and internal pressure. Each new activation adds stress. Each new jet pushes the structure closer to its limits. Ice and rock can absorb only so much strain before cracks stop closing and start propagating. At some point, and we don't know when, the internal structure may no longer be able to adapt. Pressure may escape faster than the nucleus can redistribute it. Spin may become unstable. Structural integrity may fail. That's when "not stabilized" stops being a technical note and becomes the prologue to something far more dramatic. Right now, we don't know which future awaits this object. What today's data tells us very clearly is that we are not at the quiet end of the story yet. The heat is still moving inward. The pockets are still venting. The spin is still changing. The orbit still needs that evolving push term. The coma still shows fresh structure. 3I Atlas came from another star system. It formed around a star we may never identify. It survived billions of years in interstellar space, only to experience an extreme solar encounter unlike anything in its past. Now, as it moves outward again, it refuses to behave on schedule. Every day without stabilization brings us closer to learning what these interstellar visitors are truly made of, and what happens when you push them beyond their comfort zone. The teams monitoring this object are watching constantly. Brightness, rotation, orbit, structure. Waiting for the moment the data finally commits to one path or the other. So if you want to see whether tomorrow's update finally shows those curves bending toward stability, or whether 3I Atlas decides to rewrite the rules yet again, stay tuned. Because this story is not over, not even close.